All right, welcome everyone. And today we're very happy to have Shotaro Makisumi from Columbia/IAS to tell us about working with curvature. Go ahead, Maki.
Thank you, Melissa, for the introduction, and thanks to Ben for the invitation. So let me start with a little bit motivation. I work in geometric representation theory, especially modular geometric representation theory. And the modular part means I'm working with a field K of coefficients that might be positive characteristic. And the geometric part is often representation theoretic information can actually be found in some geometry. Let's say X is a complex variety. And oftentimes, this space comes with a nice torus action. And under nice conditions that I won't talk about, there's a setting called the mixed modular derived category that's been fundamental for some recent advances in my field. If you're not familiar with this, it doesn't really matter. But something that might be a little bit more familiar to some of you is the homotopy category of Vogel bimodules. You can think of this in some cases as an example of this mixed modular derived category. So here this is the so-called Hecke category associated to some connected complex reductive group G and a Borel. So this is a really important category, an important family of categories, but this D mix is unfortunately in some sense hard to work with because it's not completely geometric. These parity sheaves that this theory depends on is not always defined. And so it's hard to for example, define what does it mean to have a perverse object in this D mix, or to define various sheaf functors in the classical theory, unless those operations already preserve parity sheaves. And so recently we've had to come up with a bunch of substitutes for these things.
Hey, Maki, I think there's a bit of an audio, like it sounds like a headphone scraping against something. Do you know where that is?
It might be headphones scraping against my scarf. I don't know.
Okay.
We can try something.
This sounds better now. So
okay.
Yeah, I'll let you know if there's any other problems. Thank you.
Yeah. And so a very good slogan has been to try to substitute geometry where it's not available with some homological algebra or category theory. And this has been really, really effective, especially in modular representation theory, modular geometric representation theory, precisely because some important characteristic zero tools are just not available anymore. So as an example of this, let's take a space X again with an action of a torus T. Then, well, this D mix T equivariant, whatever it is, it's supposed to be something like T equivariant sheaves. And so objects in this category have an action of torus equivariant cohomology of a point. That's just a polynomial algebra after you fix bases. And you can soup that up to say, in fact, you have this whole monoidal category of R modules, some suitable class of R modules, and acting on D mix T equivariant as a module category. And whenever you have that setting, well, inside a monoidal category, you can talk about an algebra object or co-algebra object, say A or C. And then it makes sense to speak of modules over such things, co-modules over such things in this D mix T. So this is a purely homological way of producing from this original category D mix T some new category of modules, co-modules. And so far this looks like a completely random thing you could do, just some weird homological operation. But for special classes of A and C, this actually turns out to have some geometrical meaning, or it seems to give you some approximations to a geometrical meaning. So here's, I don't want to explain everything on this page, but so there's something called the Koszul duality phenomenon for this Hecke category, which interchanges connected reductive group G with its Langlands dual group G check. So And I want you to compare very briefly the characteristic 0 result and the characteristic P result. In both cases, the left-hand side is supposed to be the Hecke category for the Langland's dual group. Whereas in characteristic 0, the right-hand side was something associated to G, but the category itself was something geometrically more complicated. Especially these notations that I didn't describe are quite involved. To make sense of this hat takes like a 20-page appendix or something, and it still intimidates me. Ji-Wei Yun is my PhD advisor. So I have been trying for a long time to demystify this right-hand side, since I tried reading this paper when I was a grad student. And with these authors, I think we've now really arrived at a more or less final looking answer. This right-hand side, you can actually phrase in terms of these bimodules over some algebra. In fact, it's derived bimodules for a certain very nice algebra K. So I'll come back to this, but this kind of construction really does appear naturally. So I talked about algebra and coalgebra and modules over them, but more generally, you can consider algebra or coalgebras with curvature, or even CDG, curved DG objects. And in some recent works in my field, one particular CDG coalgebra, let me call it gamma, you might recognize this curvature if you're nearby things that I do, has been appearing in several different places. And a few years ago, I became completely obsessed with trying to get down to the bottom of this mystery, and especially to try to connect the different appearances of this curvature. So with some help from Matt Hogancamp, I think I now really understand what's going on. But today I don't want to say very much about the applications. So this is just motivation so far, and today I just want to focus on telling you some, in some sense, very basic things about how does curvature arise naturally in homological algebra? How do you work with them? And then a little bit about why this particular CDG coalgebra gamma seems to appear naturally in modular geometric representation theory. Okay, so that's introduction. So how does curvature arise naturally? Let's start with the classical curvature 0 case. So this is something we all know. Complex in an additive category A. Of course, it looks like this, but let me package it in the following way. First of all, I have an object X, which is a Z-graded object in A. So that means there's an X to the I an integer. And then delta, the differential, I package into a degree 1 endomorphism of this Z-graded object X. So for a Z-graded object, it makes sense to say that the endomorphism has degree 1, and I ask that it squares to 0. Okay, and these things form a DG category with this differential. But I want to break down this familiar procedure into 2 steps. What we're doing really is you start with A, and then you go to this graded category of Z-graded objects in A. And then from here, there's some maybe a little bit less familiar operation called TWA, which somehow adds differentials. So, I mean, you can imagine, at least in this case, what this operation should look like. So just to make sure we're all on the same page, because I will upgrade this in a little bit. So by a graded category, all my gradings are Z gradings. I mean category enriched in graded K modules. So my morphism spaces have a Z grading. And a GG category is a gridded category in which each Hom space has a degree 1 differential satisfying this Leibniz rule with respect to composition. And this TOA operation, given a gridded category C, it spits out a GG category, TOA of C, whose objects are pairs, just an object in the original category together with a degree 1 endomorphism satisfying that squaring to 0. Okay, so if you set C to be Z-graded objects in additive category, then this is exactly what we were doing before. So far, so good. Please let me know if anything is unclear, because I will only try to complicate things more and more as I go on. So now let's ask, what is the TOA of a GG category? So in other words, let's say you start with a category in which the objects already kind of have a differential. In that case, how should you try to add an extra differential? So here's an example. Let's say you already start with some complex of objects in A. So alpha is already a differential, it squares to 0. And now I try to make a new differential, alpha plus delta. Then what is the condition on delta for this to really be a complex? Now, of course, this needs to square to 0, and alpha squared is already 0. And these cross terms, you can reinterpret as the differential of the new differential delta if you regard delta not as an endomorphism of just x, but as an endomorphism of x equipped with this differential alpha. Okay, so we arrive all together at this equation, probably familiar to many of you, called the Mara-Cartan equation. So it's the notion of a twisted complex in a DG category. C is a pair consisting of an object in C together with a degree 1 endomorphism satisfying this equation. Okay, but again, you should think of this equation as saying, what is the condition on delta for it to be kind of an extra differential? So these objects form a new DG category called 12C. And the new differential of this DG category is, well, so it looks just like the differential that you see in complexes usually, but there's an extra term because you already started with some category C, which is DG, has its own differential. So this operation TOA actually extends to a two-functor from DG categories to DG categories. And you should think of it as a kind of closure operation, just like taking an additive envelope or taking adding all grading shifts. So for example, the DG category of complexes was obtained by applying this TOA procedure. So it already has twists. It's closed for this TOA operation. And more generally, if you apply TOA twice, then the resulting DG category is naturally equivalent in some suitable sense to just applying it once. And here's the map on objects at least. You just add the differentials, just like in the motivation for Mara-Cartan. Okay. So you often hear this word pre-triangulated DG category, but you can phrase that definition as saying it's just a DG category that has that's closed under certain operations. It's closed under direct sum, grading shifts, and also certain twisted complexes called cones. So what's a cone? Well, if you have an X morphism F from X to Y, then a cone is a twisted complex on X direct sum Y. So that morphism F plays a role of the differential in the twisted complex. So how does curvature appear now? I consider something even more naive than complex. A pre-complex is just like a complex, but no conditions on the differential. It's just a degree 1 endomorphism delta. What kind of a category do pre-complexes form? Well, so here's the calculation you have to do. If I have two pre-complexes and a morphism between them, and if I define the differential D as before, you can see the definition in parentheses here. So it's the usual kind of definition. If you apply the differential twice, you see, because delta squared is not 0, it doesn't vanish. So this is not a DG category. So I've written Z for delta squared and Z prime for delta prime squared. Let me define the curvature of a pre-complex as just delta squared. So a complex is a pre-complex with curvature 0. Okay. Pre-complexes form what's called a Cdg category, a curved DG category. Here's the definition. In addition to the differential you have in a DG category, each object now has a special endomorphism of degree 2 called curvature. We denote that by Z sub X for every object X. And this data satisfies these axioms. So the last one is the familiar Leibniz rule, but the second one, which in a usual DG category would say D squared is equal to 0, now gets replaced by this equation involving a curvature that we saw before. And then there's maybe this slightly harder to motivate equation saying that the curvature is closed. Now, the reason why you don't see Cdg category often is because, so it is natural in some sense, but it's for many applications it's too naive. So for example, because D squared doesn't vanish, it's not clear how to understand the cohomology category because image doesn't lie in the kernel. But you can, for example, restrict to objects of curvature 0, and that's a DG subcategory. Or you can restrict to objects of some other fixed curvature, and that might give you some other nice DG category. So this is something that arises naturally. Now, let me try to motivate this first equation a little bit. So I'm going to skip this. So this definition of a Cdg category looks kind of random, but it's actually part of a much larger pattern. And for this, I want you to now think of C not as a category, but just as a collection of objects and graded morphisms, but no information about the identity morphisms, no information about composition. Now, any category has a composition, of course. So here's my picture. I think this audience is fine if I draw this without any explanation. My diagrams are bottom to top. So composition is a degree 0 morphism from C squared, C tensor C to C. The differential is a degree 1 morphism from C to C. Let me draw that like this. Okay. And so if you follow this pattern, the curvature is a degree 2 morphism from C to the 0 to C. Now, it's a little bit unclear maybe what C to the 0 should be, but if you think about how the unit works, you realize that this should be exactly what I said before. It's a special endomorphism of degree 2 associated to each element, each object in your category. And you can extend this pattern the other way too. So there's a notion of a curved A infinity category where now you have some operation that takes three morphisms, F, G, H, and defines a composition, even higher compositions. Okay. And you have the unit. And of course, this data is supposed to satisfy some relations. And they're exactly the stash of relations for an A infinity algebra. So let me try to write some of them. So for example, here is the stash of relation with three inputs where I've ignored any higher compositions. Okay. With two inputs, this says if you take the differential of F composed with G, that's the same as this. Okay, so notice in both these cases, these equations are all quadratic in the sense that you're taking two of these operations and you're basically setting equal to zero some linear combination up to a sign of all the quadratic relations you can write down with the same number of inputs. Okay, so if you follow this further down, this relation looks like this. One input. And finally, you have zero input. Any questions? So I don't want to explain the signs, but they come from suspension. When you try to actually rewrite these things in terms of more A infinity language. But the point is that this CDG, all it is really, you're taking the usual definition, kind of the correct thing you could write down for a curved A infinity category, and then you just truncate it from 0 to 2. Okay, so now I want to do the same thing, but not for a category, but algebras and modules. So here's a warm-up. Let's take a monoidal category C, and let's take a module category over it. Let's call it M. As I was saying before, there's a natural notion of an algebra in a monoidal category and then a module in a module category over this algebra. If my algebra is A, I'm going to write A mod in M for this category of modules. And these are all definitions that I think everyone can write down. But now if you understand this, the definition of a CDG category, then you can just do the exact same upgrade that we just did from category to CDG category and update these notions to CDG. So for example, here's the notion of a Cdg algebra in a monoidal DG category. And it follows exactly this pattern that we had before. This is a quintuple, an object A together with, so the DG part is, well, first of all, you have a multiplication of degree 0. Then you have a differential of degree 1. well, differential in quotation mark. But now in addition, you have a curvature. And this is, it amounts to a degree 2 element in your algebra. If your algebra is an actual, let's say, algebra or a field. And this data satisfies, again, the static relations. For example, here's what I had earlier. Okay. But notice that now on this left-hand side, I have the same kind of expression that had appeared in Marr-Cartan equation. And this is because I'm working in a category C, which already has a differential. So you could even soup this up even more, try to understand what is a Cdg algebra in a monoidal Cdg category and so on. But it's a good brain fortifying exercise, I think, to try to write down what the other axioms of this definition should be. Okay, let me come just a little bit down to earth. So, I mean, this is the classical example of a Cdg algebra as introduced by Posiselsky. If your monoidal DG category is graded K modules, viewed as a DG category with 0 differential, then a Cdg algebra in this monoidal DG category is nothing but let's call a Cdg algebra. So this is an algebra A, graded algebra A, together with differential D and curvature H. H is a degree 2 element satisfying these two axioms. So again, D squared does not have to equal 0, but D squared is given by commutator with this special curvature element H. So one example that often comes up is you can just take your curvature H to be central in your algebra. In that case, this commutator is 0. And so you can take the differential to be 0. Now, just like with a Cdg category, it's not clear how one should extend the notion of a quasi-isomorphism of DG algebras to the Cdg setting. And one should really be careful about model structure and divide category and so on. So there's a similar definition of a Cdg module or co-module. A left Cdg module over some Cdg algebra A in a module category M is such a triple. It's an object X in M together with a degree 1 endomorphism delta, and then another morphism of degree 0 encoding the action. And this satisfies the Stasheff identities. So again, for example, the associativity comes also from the Stasheff identities. It's just the Stasheff identity with 3 inputs. The most important axiom is, again, this one. So on the left-hand side, you have this Marr-Cartan type formula. And it's not equal to 0, but it's given by left multiplication by the curvature of A. And Cdg modules form a DG category. It's a little bit painful exercise unless you set it up correctly. But straightforward. There's an even more general object called QDG modules, which have their own curvature. And such things form a Cdg category. And those are useful too, it turns out, for certain things I wanted to do, but I don't want to talk about them. Those things are also in works of Posiselsky and Polszczuk. So here's an example. You you've probably seen before. I've been working with Z-graded Z gradings, but you can use a Z-mod2 grading if you want. And then you can follow through the definitions. Let's take a Cdg algebra of the following special form. It's just an algebra supported in the even part and zero differential. And let me rename the central curvature H to W. It's supposed to be potential. Then the module over A is nothing but a matrix factorization. Okay, so M is supposed to be an R module. There's no condition about a differential because D is 0 here. But D squared, the differential D on this module M satisfies D squared is equal to W. Okay. So you might not think of this as being in the same family just because this differential is 0, but really the key takeaway is that in all these different examples of structures that you can produce, you might have a little bit hard time actually pinning down the axioms. You might be missing some condition like the curvature has to be closed or these somewhat subtle things maybe. But they actually all come from just spelling out the Stasheff relations. In most cases, most of the relations are going to be automatic because maybe here the differential is 0, or you're working in just a DG category instead of a CDG category. So here's another fun kind of structure that I've had to work with. You can take an algebra and a coalgebra, put a curvature on both of them, and then you can consider a module co-module. So on the left, you have an action of the algebra, and you have on the right, you have a co-action of the coalgebra. And then the Stasheff relation with one input tells you this. Okay, there's a curvature of the algebra and curvature of the coalgebra, both coming into this picture. Maybe it's a good place to take a break.
Was that a CDG coalgebra or just a coalgebra?
Oh, I can take C to be a CDG coalgebra. CDG, I guess, algebra and CDG coalgebra.
Okay, thanks.
Yeah. So again, I haven't written down all the axioms, but it's an exercise to write them all down.
Okay, great. Yeah, so let's take a break until 1:39. And if Mike is okay with it, he'll stay here to answer questions. I think I'll pause the recording for now. Okay, the recording is resuming. Okay,
so now I want to tell you maybe something a bit more interesting. And this is the subject of Koszul duality for these curved objects. So let's again take a Cdg algebra A and a Cdg coalgebra C in some monoidal DG category. Sorry, that's a mouthful. I want to introduce this notion called a twisting cochain, which is some way of relating C comodules and A modules, or CDG modules, CDG comodules. And what it allows you to do more specifically is to define some new kind of tensor product called the twisted tensor product. Instead of taking two A modules or two C comodules, this will take an A module and a C comodule and tensor them together. So I want to refer to this kind of triple, an algebra A, a coalgebra C, and a twisting cochain, relating them as I just wanted to give it a name. So I call it a Moore triple after some work by Moore and his collaborators in the 60s and 70s. And this is the starting data for a framework for Koszul duality that's due to Keller and his student, Lefebvre Hasegawa. So I really don't want to maybe dwell on this definition of a twisting cochain, except to say that this again is some kind of Mara-Cartan equation. There's a tau squared here, and this is differential of tau. But it seems better to just show you how this twisted tensor product works. Let me come back to this example in a bit. So I have a right A module, say, and a left C module. The usual tensor product would be, okay, so I know how to take a tensor product of the underlying objects, unbolded X and Y. And each of these X and Y has a differential. And this is the usual differential that you would write down on a tensor product, right? But that's not it. You add this extra term, which comes from the twisting cochain. So let's just understand what this picture says. So this left-hand side is an X, this is a Y. Okay, so starting from the bottom, I can use the coaction, the right C coaction of Y to split out a C. So this bottom thick strand is a C. And then I have a twisting cochain, which takes you to an A. And then I use the right A action on X to swallow that back into X. And tau is a twisting cochain, it's degree 1. So this has the right to be something like a differential. There's a slight sign difference depending on if you're doing an A and a C versus a C and an A. But otherwise, this is the definition. And this gives you, so it really behaves just like the usual tensor product. It gives you a DG bifunctor on categories of Cdg modules and Cdg comodules. If you have extra actions, so in addition to maybe if X had some extra action on the left and Y had an extra action on the right, and those things just come along for the ride in the twisted tensor product, and so on. So in particular, you can take the regular bimodule A and the regular co-bimodule C and take a twisted tensor product of them together, and that will give you something in A module C co-module. And this will be a Cdg. It will have the right curvature condition.
Sorry, so this left,
Yeah.
so extra left and right actions, so they should interact nicely with tau, or there is no kind of relation with tau?
So
if X is
well,
the left module for some other algebra, like CP, whatever.
right, yeah. So I guess I'm saying X should live in a bimodule category for C or something, really. So already the left action and the right, so that already says the left action and the right action somehow commute up to isomorphism. Yeah, no condition with tau. It's all kind of encoded in being a bimodule, X being a bimodule or Y being a bimodule.
Okay.
Okay, so the title of this section was Koszul duality. I still don't know how to say. I haven't decided what the right pronunciation of Koszul is. So please excuse my fluctuating pronunciation. So there's this very classical symmetric exterior Koszul duality. And the form that takes in this new setup where there's instead of two algebras, there's an algebra and a co-algebra, is that you can, for example, leave the exterior algebra as an algebra, but then you take the symmetric algebra and you take its dual. Well, you take its graded dual, and that turns it into a, well, it has the same size as a polynomial algebra, but now it's a co-algebra, and it's a, you should really think of it as a divided powers co-algebra. So this co-multiplication is dual to the multiplication on a polynomial algebra. Okay, so this is how the picture, I mean, all this example is for an exterior algebra and a symmetric algebra in one variable. And in that case, here's what this twisting cochain looks like. Let me refer to this as the BGG triple. And of course, you can do this for exterior algebra of any finite dimensional vector space over K. Okay. Now, starting from just this triple of A, C, and a tau connecting them, you always get a DG adjunction relating C comodules and A modules. And here's how it works. Well, if you have an A module, then it now makes sense to tensor on the left with C because you have a twisted tensor product. And that carries you to a C comodule. Then you can also go back by twisted tensor product on the left with A. And it's really, really easy to show from the definitions that this is always an adjunction. Now, there's a really particularly nice situation that happens sometimes and happens for us, is that this adjunction, when you pass to the cohomology category, is an idempotent adjunction. This means that, well, it's not an equivalence, but any adjunction restricts to an equivalence on some subcategories. And these subcategories are really easy in this case. It's just the essential images of these functors. So if you do this, that's not an equivalence, but if you go 3 times, that's an equivalence. The same the other way around. And this condition seems to be very closely related to Koszul duality in the sense of Keller, Lefebvre-Hasegawa, and Polzicelski. But when they say Koszul duality, they really mean some equivalence of derived categories or some versions of derived categories. And in general, when you're dealing with curved objects, you don't really want to consider like at least the usual notion of quasi-isomorphism. You can't. So you have to phrase this carefully. So I don't know that I want to say how precisely this condition is related, but yeah, it is closely related. So the way you can think about this is that these functors are kind of resolving each other. So you can start with an A module, and then by tensoring with C on the left, you're taking some kind of resolution. And if this idempotence condition holds, you should think of this as saying something like you can compute inside here to carry out computations in the derived category of A modules. Okay, let me not say anything more about that. I can say more if
Hey, Mackie.
you're interested. Yeah.
I'm sorry to bug you. There was a question in the chat, which is,
Sorry, yeah.
are A and C curved in this previous slide?
Yeah, that's what makes it hard to talk about the derived category.
Can you go back? Because I'm also confused.
Let me try to go back. Sorry, what was the?
So Vanessa was asking, what's the H0 mean?
Yeah. So
Yeah. So
So
yes.
what's the differential on A mod C?
Thank you. Yeah. So A has a curvature, C has a curvature.
Yeah.
But Cdg modules form a DG category.
Okay. Okay, what was the differential on that again?
The differential is this twisted differential that you have in that I defined in tour, I guess. So yeah, a Cdg module is equipped with a differential, and you use that to define the differential of this category of Cdg modules.
Ah, okay, because the curvature only comes into play when you look at the module structures, but
Yes,
okay.
that's right. That's right.
So the curly C was just a DG category.
Yes, even
Yeah.
if yeah, that's right. That's right. Yes. Yes.
Okay.
C is just a DG category.
Yeah, thank you.
Yeah. Okay, so this idempotent seems to be especially clean way of trying to at least approximate Koszul duality when everything is curved. It's hard to talk about the right category. So applied to this BGG example, this phenomenon really does recover the classical symmetric exterior derived equivalence of BGG. Okay, so this is what I was saying before. So now so far in this BGG story with an exterior algebra and the dual of a symmetric algebra, there was no curvature. But now I want to tell you how the curvature arises. So I was working over a field K, but now we can deform this whole story to a polynomial algebra. And this R is the same R that I had at the beginning of the talk, the T-equivariant homology of a point for some torus T. On the algebra side, the exterior algebra gets tensored with R, and then I equip it with a differential so as to make the Koszul complex, which is a DGA resolution of the trivial R module. Then it turns out that on the coalgebra side, after tensoring up to R, you should place not a differential but a curvature. So let me not explain what exactly this notation is. I won't have time to flesh it out anyway. But this is due to a key insight of Pozitselsky, who realized that in generalizing the theory of Koszul duality, when an algebra doesn't have an augmentation, some DG algebra map to the base field or ring, then on the coalgebra side, you have to actually compensate for that by placing a curvature. So why do we care about this deformation? Well, I just told you that the Koszul complex K is a DGA resolution of the trivial module. And so it's something that takes an R action and just kills it. I mean, it kills the action of the augmentation ideal of the polynomial algebra. And this corresponds to, in geometry, this is supposed to be like forgetting the torus equivariance. So in favorable situations, if you start with this D mix T equivariant category from the introduction, and if you pass to the category of K modules, then this recovers the same category D mix, but not T equivariant, but T constructible.
So we have this equivalents as monoidal triangular categories?
Triangulated, but in general, this is in general these things are not monoidal.
Okay, thanks.
So this deformed triple, the deformed BGG triple, at some point I started calling it the Cartan triple. It's still Koszul in some sense. So to make sense of this is a little bit difficult because now you're not working over a field anymore, and so you have additional model theoretic difficulties apparently. But this is the work of some ongoing project of Jesse Barker. But actually, we take a different path. So Matt and I just stick to this notion of a homological idempotence of a triple. Show that this triple continues to have that property after this deformation. And so the upshot is, well, we care about K modules. Oh. I don't seem to be at the point anymore, sorry. Okay, so we care about K modules. And we actually sometimes even care about derived K modules. As in this Koszul duality slide that I had in the motivation. And you can compute derived K modules by first passing to Cdg modules over this Cdg coalgebra gamma, precisely because of this causality or homological idempotence. And in the same kind of vein, instead of trying to work with derived K bimodules directly, we can first resolve and work with Cdg left K module, gamma right comodules. And two such objects can be tensored together using the twisted tensor product by using the right gamma and the left K. And that actually corresponds to the derived tensor product of the corresponding K bimodules. So this is why secretly in all these papers that I had mentioned, this curvature showed up. It really was just, they were implicitly working with the Cdg coalgebra gamma. And so they were secretly working with some sort of derived bimodules for this algebra K. And once we understand the role of this curvature actually correctly, then in some instances, this seems to really simplify the argument. So I'm trying to write some of this up. Well, maybe not any shorter, but much cleaner, but still long papers with Matt. I'll end there.
Thank you so much. Let's give Mikey a hand. All right, are there any questions?
Well, I might have missed this, but could we go back to your main example of your CDG?
So I didn't say. Is this what you're talking about?
I'm not even sure if you showed your main.
Yeah,
example.
I didn't show the main example because it's I won't be able to get into it anyway much.
Okay.
So I can just say verbally what a little bit more what's going on if you're interested.
But if it's going to take more time, then maybe let's receive others' questions first.
Okay, yeah, sure.
Hey, can I ask a stupid question? Sorry, this is Nitu.
Hi.
Hi. I'm trying to create an analogy in my head And I was hoping maybe you have some insight into this analogy. And so what I want to do is to take your algebra and turn it into the geometry that if I could. And the way I want to do that is a little different from what you said. Maybe it's similar, but if I have some principal G bundle on a space and I can look at the space of all connections on it, as opposed to the space of flat connections on it. The space of all connections is contractible, so it doesn't have any interesting information. But clearly the space of flat connections, which is the Mauer-Cartan condition you have, that has a lot of interesting information. So can you see your curved setting is just connections, right? And no flatness condition, just connections, and then you have those Bianchi identity and all of the other identities as part of the structure.
So I'm not sure. I don't think I'm too. I don't think I'm familiar enough with this language to really say. Certainly, people so certainly people like Poziselsky seem to have some analogy like this in mind.
Yeah, I was maybe anybody else who understands this material could give me some insight on what I should do on the geometry side to understand what you are saying on the algebra side. I said it was a stupid question, sorry.
No, I think it's, I mean, it's the kind of thing that probably once one really understands is very helpful. I would like to understand it too.
Can I ask an easier question also relating to geometry? So if I think of lambda as the homology of the torus, really?
Yeah.
And like R and gamma are both homology of BG classified space of the torus?
Sorry, in gamma?
I don't know. Like, I mean, R, should I think of R as homology of like BT?
There's one
Yeah. I guess, yeah, just BT.
Okay. So what about gamma?
Gamma, well, I mean, so
like B of the dual torus in some sense.
B of the dual torus.
Maybe it's homology if you're using, if one is an algebra, one is coalgebra. That
yeah, it's a coalgebra. So
very naively, one could be homology, very naively.
Yes, I'm not sure, but probably something like that.
So the Koszul complex that you have here is just the kind of the rest spectral sequence for ET, right?
Yeah, that's right.
And so I wonder if you have any kind of naive topological meaning of gamma, which explains what's going on.
Could it be computing the resolution for X, and so you hom out of it, as opposed to Tor? I mean, formally it's the same, but X turns the algebra into a coalgebra, right? Because you're homming out of it.
Can you say that again? So gamma is, your proposal is what? Gamma is X'd?
I'm saying, yeah, it could be that you are computing the resolution for X'd. X is the trivial module. But formally, when you do X, you hom out of the resolution, right?
Yeah.
And so when you hom out of the resolution, your natural algebra turns into a coalgebra formally.
Yeah. I mean, it really is supposed to be the Koszul dual of the Koszul complex. So I don't know. So for example, in the symmetric and exterior algebra case, you can say those are cohomology of BT and T, but there's a dual on one side for them to be Koszul dual. So yeah, I like already in that case, I'm not sure what the precise geometric statement for Koszul duality is.
I guess, so my question, so you mentioned this Langland's duality and all this fancy stuff in the beginning, but like,
yeah.
so you have this torus like R. So here R is like polynomials on the Lie algebra of the torus. So
Yeah.
I would naturally think of gamma as polynomials on the algebra of the dual torus. And
Well,
this like sum of xi yi is some kind of natural tensor on like torus, like Cartan tensor dual Cartan basically, right? So
Yes,
that's what
yeah.
it should be more or less.
Yes.
And
So
the question is like, can you make this pairing between torus and dual torus into something like?
yeah, it's something like that. But so I'm not using the right. Yeah. So yeah, this gamma is dual to not to R actually, but to R check, the Langlands dual analog of R. So exactly as you say, this xiyi is some canonical element in torus tensor, the dual. But but I think the symmetry is, so in all this homological algebra, the appearance of dual is not super mysterious, but the appearance of Langlands dual in the Koszul duality phenomenon really, there really does seem to be some interesting mystery. It's two different phenomena.
So there's a lot of questions in the chat. I'm going to stop the recording now, so let's just thank Mackie again.